me to introduce Dr. Yonatan Sompolinsky, which I'm sure you all know, who will present his talk on Kaspa L1 and L2, ordering games and MEV extraction. As one of the pioneering minds behind Kaspa, I'm sure his talk is going to be enlightening. Welcome, Yonatan.
Next slide, please. Oh, that's me. So thank you, everyone, for coming. Indeed, I disagree with many things that Monica has voiced. I'm not sure she's satisfied with that or not. Perhaps I will say very briefly that I'm indeed a maximalist of equality of opportunity and equality of, in this sense, inclusiveness of opportunity. Not sure about inclusiveness of outcome, but I didn't prepare too much on that. So I'll go on to the material topic. So I prepared the 2 slides on this topic, and I'll give you some context on my views on L2 or smart contracts in Kaspa. We've kind of brainstormed this for a long while now. I've been working with Sutton, with Roman, with Fresh Air, and kind of trying to figure out what's the right design, right architecture, right mental model, indeed, for the smart contract design. Now, I think Anton voiced this on Discord, that Kaspa has a late runner advantage. And by that he means, correct me if I'm wrong, if you know someone else has coined this term. By that, I think it reflects the fact that a lot of the previous constructions or architectures in crypto were limited by the fact that cryptography or practical cryptographic code bases were not developed yet. And in that sense, you can think of what's happening today in Kaspa as something that is pretty much nowadays consensus on many platforms. Definitely, if you read early talks about Bitcoin, there's this strong emphasis on verification versus computation. The design of Bitcoin scripting language is deliberately very limited to verification, not to computation. And we definitely are trying to remain faithful to that principle. And I will try to dive in and discuss how this pertains to our design. There's also some movement in Ethereum, on Ethereum research or architects to go back, to bring more activity to L1 and to kind of learn from the lessons of the fragmentation of L2s. This is also something we are pondering. And this is kind of a high-level introduction to the state of crypto so far, and to the I would say to our inspiration from other projects. I personally tend to think a lot and read a lot and try to keep myself rather informed on other projects, on other project architectures. There are many lessons to be learned, correct others' mistakes, learn from others' successes. This is something that I'm invested in personally and rather mentally, always to keep up with great research, great architecture, great ideas from leading researchers and devs in the industry. Let me start perhaps with something that is not, that the first topic is, part of it is not fully fleshed out, neither in my own mind, nor I think in the broad crypto R&D discussions. That is the distinction between zero knowledge rollups and zero knowledge smart contracts, or in general, yeah, the distinction between what we call internally logic zones. So the thought process is as follows. In native L1s, let's say Solana, Sui, Aptos, they implemented smart contracts natively. A developer comes, she uses the SDK and deploys of L1 and deploys immediately a contract on L1. There's no capture of L2, although in principle, anyone can develop an L2 on Solana. I'm sure some esoteric projects exist therein. However, this is not the core, the social consensus, the core coordination of Solana or Aptos, Sui, and others. You compare this to Ethereum, which is by and large, by now, largely governed by L2s, and there's this clear dynamic where L2s compete on dev capture and on smart contract capture. What does that imply concretely, and what are the second order implications? So concretely, this means perhaps SDKs are incompatible, depends on the EVM compatibility. It means liquidity is fragmented. So if I want to deposit collateral on a DeFi lending platform, I must choose between the different L2s, between Ethereum, or rather on Ethereum L1, app chains, in the broader interpretation of an ecosystem. The second order implication is that interoperability is hard to achieve. This is more pertaining to the incentives of L2s. So if you think of an L2 as a bunch of smart contracts, or more maybe as a B2B, right? So the interest of that entity is to capture as many Bs as possible, as many smart contract biz devs of smart contracts to their roll-up, to their L2. And so really, whether we like it or not, roll-ups and L2s are playing zero-sum games. Right? There's not really an incentive, a good incentive for one roll-up to be smoothly interoperable with another one, because that means it doesn't capture as much value. It allows smooth transitioning and smooth exiting out of that roll-up. So the natural dynamic is fragmentation. Again, both from a technical perspective, there's no way to atomically compose smart contracts from different L2s. And there's more of an incentive mechanism problem. Michael will, I suppose, elaborate on atomic composability, but for now, I merely mean the ability to, transact with Uni on one rollup, lend the results on Aave, use a stablecoin, a result on Aave that's deployed on the other rollup, and then use the change from a stablecoin to a third rollup. You cannot have these composable transactions. Okay, this is on the high level. How does this translate to our more low-level, concrete design questions? So assume we have a zero-knowledge verifier opcode on layer 1. So again, it's a verification centric scripting language, and L1, very similarly to Bitcoin. So we do not want to do any compute or minimal compute on L1. Now our main focus is you come to the system, you deploy a smart contract, and then the consensus, most of the L1 nodes, most of the full nodes do not need to compute your state. They do not need to be involved in storing your state. So we supposedly circumvent the state bloat size. I'll get to that in a moment. And there's just this natural, so perhaps we are aiming to have this natural dynamic where a smart contract dev deploys things on L1. However, most nodes on L1 do not need to compute it. Most nodes on L1 do not need to add resource to their validating full node. You can still run your node on a commodity hardware similar to, or something that you have on your home. It will be obviously orders of magnitude less than native L1s. So, the prime example is Solana. It's very difficult, I think perhaps impossible to run full node on commodity hardware, which is why they're able to process a gazillion transactions per second. Now, the ZK, the zero knowledge verifier opcode, should be heterogenic and specifically agnostic to the proof system you are choosing. So you can use Starks, you can use Snarks, and various versions thereof. And the challenge is, how do we ensure that different smart contracts still interoperate? So from the incentive perspective, that's very easy, because once you create a smart contract on DeFi, on the Lego of DeFi, you are incentivized to help everyone connect with you, talk with you in the same standard. So the incentive problem is easy kind of to flesh out, or to be aligned rather with the broader community of developers. However, in terms of technology, this is more tricky because you want to find a sweet spot where you're not too inclusive to any spam contract that wants to interact with you. The fees will be dealt with, but nonetheless, a broken contract or a spam contract that wants to interact with you, and at the same time, you don't want to have a central planning mechanism where you decide and gatekeep who interacts with who. So it's semi-technological challenge, a social consensus design challenge. And maybe I will discuss two particular low-level questions that we have. So one low-level question is, imagine Alice creates a smart contract on a Stark proof system. And then Bob creates a smart contract on a Snark proof system. They can also be the same proof system, but just different instances of it. And now our challenge is, how do we make sure that there's no contamination of trust between the contracts? Let's be specific. Alice can deploy a prover, or someone else can deploy a prover, a zero-knowledge prover, for Alice's contract. And now the question is, let's say Alice interacts with Bob in an atomic manner in the same round. So some user, Charlie, has created a transaction that talks with both contracts of Alice and Bob and has interconditions between them. So it creates some dependencies between them. In a normal operation, this would be okay. Michael would dive into the details of this, but from a flow perspective, there's normal operation is okay. Alice or Alice's prover posts a proof, Bob's prover posts a proof for their part of the transaction, and everything's okay. However, there's the question of what happens if Alice's prover falls, collapses, crashes, spontaneously, not spontaneously, it doesn't matter. You can think this is an edge scenario, but in fact, this edge scenario forces us to think through the dynamics of the ecosystem. So for instance, consider Coinbase as a roll-up on Ethereum. So many big teams like Coinbase, they would want to create their own smart contract or roll-up on the system, and they would not want to have any dependency between their contracts and other contracts. This is important, right? They don't want to need to care about the failure or success of other provers. And in particular, we must decide in the design how should they react when another prover fails. Admittedly, this can also be delegated. You can push the can down the road and tell them to decide it. But there's some standard that needs to be put forth, even if it's not necessarily enforced in the design logic. Two paths that we think of, that we are contemplating between. One path is that I think I'm slightly against it, which is that the second roll-up would the Coinbase roll-up, for instance, in that example, or Bob's roll-up would need to roll back its transactions if Alice's contract fails to provide a proof. Okay, again, it doesn't have to be Alice's contract, it could be Alice's prover. The details of this, it could be also permissionless, just some Zoe posts a proof for Alice's contract. There's no permissioning necessarily in the process. So one path is to roll back. So in the program of Bob's or Base's logic, it encodes the fact that if a prover for Alice has failed to interact with L1, we revert this transaction. The problem with this, again, is that even though it's a doomsday scenario, many applications, at least big applications, will not want to have this dependency. The counter argument is that these organizations will find it easy to reconstruct by themselves a proof to Alice's contract. And this is where the based design is crucial. So the fact that Alice's contract, and perhaps I should have said it in the beginning, because of Kaspa's design, all transactions are recorded on L1. The payload or the raw data is recorded on L1. Anyone that has interest in Alice's contract can record her transactions. So there isn't this dynamic, Ethereum-like dynamic, where if I'm interested in your roll-ups logic, I have to reconstruct your state. In Kaspa's design, if I'm interested in your roll-up, I'm just listening to L1, and that's sufficient for me to reconstruct your state. So the counter argument to the rollback would be, rollback in the program. It's not manual. It's more automatic rollback or automatic reverting of the transaction. The counter argument would be that big teams or developers of big families of smart contracts, or islands, as Hans likes to put it, would find it rather easy to listen to contracts they depend on, and to post a proof for their, just in case that contract's prover fails to interact with L1. Okay, so what does this debate or contemplation mean practically? If you go down the route of the following logic, namely, Kaspa is based meaning, I don't mean in the slang, only in the slang sense. I mean, Kaspa uses a based roll-up design. All transactions are recorded on L1. There's no other sequencing happening behind, closed doors or permission doors. If you go down this logic and you say, okay, the strength of the base design is that anyone can reconstruct anyone else's state when they need it. Then this begs the question, perhaps it's not trivial that it begs the question, but it does lead to begging the question, do we need to have a global cap on each state's, on each logic zones or roll-ups size, state size? So you probably heard of the state bloat problem in smart contract systems. In Ethereum, it's a more known problem. In other chains that ignore it. So the fact that it is a criticism of Ethereum is sort of a praise of Ethereum because they are aware of this. They put forth this problem. And so I think a year ago or something, we came up with a fee design to counter the state bloat problem on Kaspa and the UTXO, and just in the payment, on the payment size, on the UTXO set size, regardless of smart contract. So we call it Storm. Forgot what it stands for. Storage. What is the R? Oh, so the storage is still, the R is still, okay, storage mass. I thought you came up with something interesting about the R. So storage mass, and the question that we are fighting over is whether it's logical to force each silo, each roll-up or logic zone to restrict their state size. Let me give an example. Let's say one of you wants to create a decentralized limit order book on Kaspa. That order book would have potentially a huge state size. And the question is, if this is decentralized enough, then are we willing to force you with Storm-like mechanism or some other mechanism that one of you will post on Research Kaspa to limit your state size? And again, the pros and cons are rather trivial, but I'll spell them out nonetheless. The pros of letting you, or the cons of forcing you to constrain your size, your state size, is that this restricts your use case. You might say, well, I have in my DLOB, decentralized limit order book, I have, maybe hundreds of thousands of transactions per second, maybe tens of thousands of transactions per second. I don't want to store. I need the storage, and I have my own hardware to store it, and I'm not leaking any trust problems to L1. Then why do you force me to restrict the economics of my transaction fees? The counter argument is that for it really to be useful, or not useful, for it to really be robust or trustless, we need, if we interact with your LOB, we would want to be able to reconstruct your state, as I said previously, due to the base design, in case your provers fall. So we understand you have large servers to store and process things, and you have large, elite hardware or uniquely designed hardware to prove it cheaply and quickly. But in case your servers fall, we still want everything to operate smoothly. And therefore, we want to make sure that if your servers fall, no one else is harmed. So this is kind of the contemplation that we are having in core. I should mention something that looks like I deliberately postponing this comment to the end, but I do need to be transparent with you and say that all of this is due to our insistence on sync atomic composability, meaning on the synchronization and the interaction between different rollups or different logic zones being sync, meaning in the same transaction you can interact and post conditions among different rollups. Meaning that even if you happen to hear that I have overstated the challenge and that this can be solved simply by using L1 as a bridge, that would be correct, but that would mean giving up on the synchronized ability to interact between different logic zones. And this is a compromise that I, at least, am pushing against. I think one of the main value propositions of DeFi, especially if you compare it to TradFi, is the sync ability, that you can sort of use things as a Lego box. Again, if you operate in silos, this kind of rolls back the value proposition of DeFi. This is an argument that others can push against. Many thought leaders in Ethereum ecosystem definitely explicitly pushed against this and argued that sync interoperability, sync atomic composability is overrated. I have steeled man the argument for against this, and I still stand behind it. But I just want to be transparent that there's also a compromise that others and on Ethereum definitely others have made, that we should be okay with async. Okay, so that's one topic. I won't touch onto the miners versus real-time proving. Maybe I will touch. I just mentioned very briefly that one path to solve all of this, to address all of this, is to delegate the dependencies to miners. This is mentioned as a remedy. I'm not sure it is. It depends on, again, on the point below it, on the enforcement of a global state cap versus a local one. Because if you push everything to miners or to any entity, then you're sort of forced to introduce an agreed upon consensus enforced cap on state size and other resources, whereas supposedly the value proposition is that you can act in a more distributed manner. I want to touch on another point that I have seen yesterday from Aptos team. So Sherry, she's a founding engineer from Aptos. On the main stage yesterday, I didn't get her permission to take this picture, so just for respect, I put an intelligent emoji in her stead. She has posted a few or spoke about a few developments in Aptos, and the second one has caught my attention because it's something that we are contemplating in core. So in general, when you have different logic zones, and again, recall that we are recording all transactions in L1, each one of you can take, scan the L1 and reconstruct the state of any other logic zone. So recalling that, the question is, does it make sense to force the same ordering of transactions on all logic zones. The natural answer would be, why should we not do that? Why should we give each contract their own flexibility regarding how to order transactions? So there's a good answer why we should do that. And Sherry has hinted to that, and I found there one good explanation. And I want to explain why this is less trivial than it sounds. So the argument is as follows. If we want to optimize the system financially and prevent MEV, manipulations on the price, manipulations by market makers, we want to make the system more efficient, then it would be there are financial solutions from TradFi and also from DeFi, but they're rather not very sophisticated, very straightforward, at least today, to counter and make the system more efficient. I don't know if this is inspired by Eric Budish's paper from Harvard, or I think formerly Princeton, about frequent batch auctions to counter algo trading. But the idea is, if we look at all transactions in the same round, so I got 1,000 transactions to the, let's discuss the DLOB, the decentralized limit order book. I have 1,000 transactions in the round. So if we enforce a certain ordering on this limit order book, then it's rather easy for manipulators, in our case miners, to inject transactions in advance before the block is mined, so as to optimize their strategy. So this is called MEV. I'm sure many of you have heard about it, and it's easy to counter this if you just focus on the limit order book. So just focusing on limit order book, it's clear that if you don't force me to process transactions one by one, rather you allow me to view the entire batch of transactions that were sequenced in this round and allow me to pick the best price and do the best matches between users, between sellers and buyers, that will make things much more efficient. That's trivial. And there's also a paper by my advisor, Professor David Parks, and Matthews, about having more flexibility on the ordering. I think that's more regarding AMMs, not limit order books. At the same time, I want to press the point why this is not trivial and why we are fighting over this. Namely, this harms composability. This is important to understand. If you declare your own zone not interoperable, again, in sync mode, async, this is something different. If you declare your logic zone not composable with other zones, then yes, you can adopt solutions from TradFi to counter manipulations and make your system more manipulation resistant and more efficient. Good. What you lose in the process is the ability to interact with other contracts and other logic zones in sync mode, which you can be in favor of, you can reject, but I just want to make sure that we understand what the trade-off here is. This looks like an exciting improvement. This does, however, it makes a severe concession to the design, and we need to be conscious of this. And yeah, I see I ran out of time, so I will just touch very briefly on the one topic that I have neglected to mention. How do I go back? Oh, here. So finally, and again, Michael will dive into the details of this, as far as I know. there is, if you remember the MEV VM creation a few years ago, then the MEV ecosystem has split into two kind of instances. One is SUI, one is Aptos. MEV is an asset-based VM, an object-centric VM, if you may. And there is this clash or healthy battle between these projects about how best to achieve parallelism of the system. Why are we speaking about parallelism now? Is this not an over-optimization? No. There is a conceptual relationship or reduction between parallelism in how to most efficiently distribute the computation among your own cores in your computer, reduction between that and the topic that we touched on before, which is the independence of logic zones and provers. So the very intuitive reduction is, if I'm able to, if I take, let's say, 1,000 transactions in a round, let's say we're in Aptos, then the Aptos system, the block STM, distributes them or discovers their independencies in real time so that it's able to process more transactions in a more efficient manner. SUI does this in a more static manner, which is not in real time. It does it in advance, and there's different interpretations of in advance. I won't get to it now. It's called in compilation time, but in practice, it seems more related to when the transaction is issued rather than when the contract was developed. But there are nuances on this, and I'm happy to get more SUI experts, to get feedback from SUI experts on this. However, the thing we need to be conscious of is that, so the reduction is, if I can process two transactions independently on an Aptos system or SUI system, then I can also delegate this to two different provers in Kaspa. So the final statement of this is the parallelism in real time. The parallelism in L1s that process smart contracts on L1 can be reduced to the independency between different provers on Kaspa. Okay, on Kaspa L2. So this reduction is very useful when we in core are thinking about this how to borrow from these project architectures to design the independence of provers. That said, of course, ideally, you would want to choose the most optimal, which is the real-time parallelism of Aptos. But this is a bigger challenge. So the one immediate reason why this is challenging and could be a deal breaker is that in real time, in the L1, L2 dynamic, we need some pre-agreement, or an easy way at least, to get to agreement on what the computational graph independencies were. And we can't do this by referring or deferring the discovery of the computational DAG or the computational independencies in real time, because L1 nodes do not want to hear anything about L2, or at least many L1 nodes would choose to be completely indifferent to this whole topic. So if you're an L1 maxi, or you only want to focus on payments and and, in the money base, then you're probably the only takeaway message that you want from this lecture is that you can forget about it. And indeed, this is the case. So to keep this premise, we have to not allow contamination of the dependencies, or we can't force L1 to deal with the dependencies between logic zones. We have to keep this an L2 task, an L2 challenge. Therefore, it's easier to work with a static type of parallelism wherein different contracts or transactions have to declare their dependencies in advance so that L1 does not need to govern this, and in particular, so that if you have decided to create a smart contract that is completely siloed from the other contracts, let's say you have a good excuse for that, then you don't want to need to prove constantly that you're independent of this activity. You want your provers to need to be turned on, or to listen to the network only, or to interact with the network rather, only when your contract has achieved activity, has triggered activity. So this is kind of a rough overview of where Core's R&D thoughts are standing. Again, Michael is a better address than myself, at least, to know, like, to give some timeline, at least regarding, and context, at least regarding the upcoming Crescendo upgrade, which allows and enables part of this design. I will hand off the mic to him, and I welcome everyone to join the R&D, to give your ideas, to think about these things, to counter many of the arguments, and perhaps to give us more, especially the experts in the crowd, more input on how better to, or how to resolve these questions and how to optimize the architecture of Kaspa. With that, I will thank you all and see you around.